Hi, welcome back to the lecture series on base general topology. We were discussing a topic named continuous function between topological spaces. So remember that in the previous session we started our discussion of continuous function by giving some motivation how it is coming from in general metric spaces. So let's revisit. So we have started with some motivation comment, that is, suppose a metric space x to y. For example, let us consider d1 is associated metric on d and d2 is associated metric on y. So if we have any small x naught is a particular point, and then we say that small f is continuous at this particular point x naught if for any epsilon belongs to real number, and of course epsilon should be larger than 0, the f inverse of this ball of radius epsilon centered at f of x naught, of course this ball is inside the metric space y. This must be an open set. Okay, so more clearly, just it is basically a general implication of some other statement, which is basically like this. So the definition says that, if you take any epsilon belongs to real number, epsilon larger than 0, then you may consider this open ball. Okay, then there is certain delta which is also strictly larger than 0, such that the function this b delta of x naught is completely mapping inside b epsilon f of x naught. Okay, so means suppose we have a x space here and y space here. If you take any open ball here and let's say it is x naught, so this will completely coming inside this. So remember, we said this epsilon to be as epsilon neighborhood and delta to be as delta neighborhood. Okay, it may happen sometime that delta is depending on x naught, or sometime delta is independent choice of x naught. That is based on the structure of the function and all the properties of the metric spaces. But the most fundamental thing that is playing in the centrally in this entire concept is basically that pullback of any open set in the range space is also an open set in domain space. Okay, so that is a basic fundamental game that is being played behind. So this will force me to generalize the structure or the continuous function concept of the continuous function in normal topological spaces. So what is this? So just suppose we have A to F is a mapping from x to y where both are topological spaces. So it may happen that these are not blessed with a very nice metric associated with them, but they are blessed with some collection of open sets. So that will play the game, that is, suppose small x naught belongs to capital X, then we may take any open set u y which is subset of, or let's say u of f of x naught which is subset of y. This is open set, and the property is that f of x naught is inside u of f of x naught. Then the f inverse of u f of x naught, this is open in x, and of course x naught belongs to f inverse of u of f of x naught. Okay, so that is the property or the concept of topological space that we can extract from this particular fundamental idea. But remember one thing, that there should be some similarities between this one and this, means some one-to-one identification. So one-to-one identification is basically via metrizable topological space. In this setup there is one-to-one correspondence. So you see one thing, okay, so and if f is continuous at each x belongs to x, then f is continuous in entire x. Okay, so you see one thing, that suppose we have x comma d is a metrizable topological x comma is a metric space, and y comma d2 is another metric space. Okay, so then suppose we have function f from x comma d1 to y comma d2, but as well we can cook up with topological spaces x comma tau d1, which is metrizable, which is basically induced by the metric d1, and y comma tau d2, which is induced by the metric d2, and we can have the same functional mapping like this. Okay, so then both the definitions are equivalent. So definitions, so what are the definitions? Once you consider these to be as a metric space, then you will have metric space property, and once you have a topological, you can see it is a topological space, then you have topological space definition. So both definitions are equivalent. Okay, so of course in this case one side is very clear that topological space property space definition which is associated with a topological space, that is if you pull back of any open set, this is also an open set. This of course amplifying the first one, the metric continuous function gives up as a metric space. Okay, because once you have any ball, that is of course open set in the topological space as itself. But what about the reverse one? The reverse one is also very easy. Suppose u of x is a metric space. I mean suppose u is open set in y, so then we can write u to be as a union of all, let's say okay, not u as let's consider that suppose small x belongs to capital X such that fx belongs to u, so there exists epsilon belongs to a real number larger than 0 such that b epsilon of fx, this is inside u. Okay, now if we take the inverse of this, so f inverse b epsilon of fx, this must contain small x, and this is subset of f inverse u. Okay, so f inverse u, now we can write f inverse u to be as union of all small x belongs to x such that fx belongs to u, and is nothing but f inverse b epsilon of fx. And we have already from the first property we have that this is open set. Okay, so this is open set. In fact, we can write v as some suitable in terms of some suitable deltas itself. So fx belongs to u, so it is some suitable b delta x. This delta may depends on x itself. Okay, so these are the open balls, so that means f inverse this must be open. I mean because in each of these f inverse, this can be written as in sum of b delta x's. Okay, then we are done. All right, so that means these metrizable topological spaces, these have some beautiful beautiful property that can work as a bridge between two particular definitions. In fact, we will see in later cases that, in fact, we will spend some time on this, because once you have a topological space and the topology, but you may get some suitable metric that can induce a topology, then it is very easy for us to handle with the topological space, because it has some more properties and we can use some more basic tools over there to understand and analyze the topological spaces. So that's why we will study, spend some more time in later cases on this particular topic. So, but let us move ahead. Yeah. So you see that it is in case of metric spaces, it is enough to define the topological define the continuous function over some basic open sets. Because it was open walls. Now you see that these metrizable topological spaces, the open balls, these are nothing but the basic open set. So this concept also as well as can be extended in case of normal topological spaces. That means there is a corollary that suppose f is a function from let's say capital X to Y. Okay. So once you have any topological space, then of course you have some basis of that topological space. Then if is said to be continuous if and only if for any basic open set by of y, we have f inverse by, it is open in X. Because you see that if you have, let's say, any open set V, you may write V as union of all small v belongs to capital V by. Every open set can be written as union of some basic open sets. So F inverse this V, nothing but union of all F inverse by. Sorry, by. Okay. So this is must be open set. So it's very trivial. But the question may appear that are they basic open set? So from this property you can see that F inverse be an open set, but who is given a guarantee that F inverse be is open basic open set? So for as a counter example, let's consider that if is a mapping from R to var such that let's take a constant function f of x equals any particular smaller is a constant function. Then any basic open set f inverse any open interval a comma b is either R or phi. So R if smaller belongs to a comma b, or phi if smaller does not belongs to a comma b. Okay. So, but can you give some fruitful forward example, like when it is true? So for true case we may assume that if it is a mapping from R to var such that fx equal to x itself, then f inverse of any open interval a b it is itself a comma b. Get done? Okay. So continuous functions are also a very useful tool to check which topology is weaker or which topology is stronger once a topology, two different topologies are applied in the same underlying spaces. So suppose we have let's say x is underlying space equal to phi. Let f is a function from x comma tau 1 to x comma tau 2. Okay. So this is such that if using identity map, so then tau 1 is finer than tau 2 if f equal to identity is continuous. So that means, because you see that suppose if this function has to be continuous, then that means for any let's say basic open set f inverse u, if u is subset of x and is open in tau 1, so f inverse u is itself u, this is sorry, it is tau 2, so it is open in tau 1. So that means tau is subset of tau 1. So that means tau 1 has more open sets. In fact, you can, if you take any basic open set, then it is also basic open set over there. I mean, it is open in there. Okay, so that means it is universal open set. So that means it is finite topological spaces. So as an example, suppose let's consider x to be as R, and let us take tau 1 to be as normal equivalent topology, it is tau ed, and tau 2b to be as tau lower limit topology. So tau ed is basically generated by then we can write, I mean, we know that tau L, this lower limit topology, is basically generated by open sets of the form a comma b, such that a is strictly less or equal to b union with r comma phi itself, and these are generated by a comma b, where a is strictly less than b. So these are open set, and this is one open set, clear open set. All right. So you must see that every open set a comma b, this can be written as union of all n belongs to natural numbers a minus 1 over n comma b. So this one can construct this map. So in fact, these are the open sets in r comma tau L. So this entire is open in r comma tau equivalent topology. Okay. So that means the identity function identity over from r comma tau L from r to tau ed says that this is continuous. Okay. So all these properties we have seen in the last session. Now let us move ahead with some more advanced exercises. So there is something called just a second please, let me have a double check with this. Okay, suppose X be a topological space and we consider a real world function from X to R, and we of course induce the normal equivalent topology on R. Then let's say F is this and G is from X to R, maybe, or we can define C itself as well. Okay, whatever, R or C, whatever. So then we always can define the addition of two functions f and g such that f plus is defined from x to r or whatever we see, such that f plus g of small x equal to fx plus gx. So in fact you see that fx and gx both are maybe real or complex numbers, so the addition is always possible. Similarly, you can define the multiplication of these two maps f dot g over x is nothing but fx times gx. Now the question is that, so if we have f and g continuous, then f plus g and fg both are continuous functions. Okay, so suppose we consider, it is very easy to check that suppose we take small let's say any open set U is open in R, so there exists some epsilon by 2 belongs to, so let's say epsilon belongs to real number, epsilon larger than 0, such that in fact you can choose for any epsilon by 2, for any by 2 belongs to real number, and epsilon then 0 you could consider b epsilon by 2 of x of any open set. So let's say sorry, f of x naught. I'm sorry, yeah, b epsilon by 2 of f of x naught. So this is an open ball in y, okay, or not y, it is, let's say, in R. Okay. So we take any x naught belongs to f in f, let's say f let's say capital X itself, maybe capital X as that f of x naught, this belongs to U. Means, what we have to choose? Okay. And again, okay, so not, let's say, not take f of x naught, rather, what you have to show, that you have to take any open set from this one, take any open set from this one and show that inverse image of this has to be in x, right? So that's what we will do. That suppose we consider any open set b epsilon of, let's say, b epsilon a of any small y, let's say, is any basic open set, in let's say R. So suppose f inverse of b epsilon of y, this must be open, right? So as it is open set, so this must be open set. So let we consider that small x naught belongs to f inverse b epsilon of y. So f of x naught, this belongs to b epsilon of y. So for this x naught, I consider an open ball, let's say delta 1. There exists some u1, which is subset of x, and this is open, and f of x naught, this belongs to b epsilon of y. Okay, let us make it half. For instance, let us make it half, because this is my open ball. So we can make this open ball more shorter, like this, epsilon by 2. So that means modulus of y minus f of x naught is less than epsilon by 2. Okay. So again, there exists some u2 subset of x such that y minus g of x naught is less than epsilon by 2. So that means we define that, so f plus g of x minus f plus g of x naught is less than epsilon once you consider the u1 intersection u2. So this b epsilon of small y, this particular open ball, is nothing but f inverse of this is nothing but u1 intersection u2. Okay, so this is how one can define the open set in case of addition of two functions. All right, but similarly one can define the product of two functions. So product is You can take it as an exercise. Product exercise. I mean, nobody is going to ask you to prove it, but for your own understanding, this is good to verify the product one. Now, suppose there is also another beautiful corollary that, so we have seen that continuous function can be used to characterize the uh, strength of a topology. Like if we have any topological a basic, I mean this one, that if we have any particular non-empty set and different topologies tau 1 and tau 2. So suppose tau 2 is something is stronger than some other one. So continuous function is very helpful to uh, helpful for you to check which is stronger, which is weaker. So similarly, is another application of this continuous function is the following: that suppose we have a feature mapping from X to R in the topological space. Let's say G and F, these two are continuous functions. Then we consider that A to be as set of all small x belongs to capital R such that fx is strictly less than gx. So this is open in X, and this set belongs to R such that fx is less or equal to gx. So this is closed in X. So you see that, suppose, in fact, this is generalization version of this, because once this is open, so that means B complement is nothing but x belongs to R such that fx is strictly larger than gx, and you already proved that one side is open itself. Okay, so how to prove it? So suppose I'm sorry, not, it is said to be capital X, yeah. So we will use this via the property of openness. Okay, so what is A? A is basically, can just write it as gx minus fx is strictly larger than 0. Okay, so we can write A to be as some inverse image of some open set. Okay. Suppose we consider that gx, I mean, you see that G is continuous, right? That means minus of f, and f is continuous, so as f is continuous, so minus f is as well continuous. So, and G is continuous, means G minus f, this is continuous. So as it is continuous, then what we can define, that we consider that R to be U to be as R is strictly larger than 0, means it is 0 comma infinity. Okay, so this F inverse U, this is itself A. Okay, so this is open set. When this is open in R, this is open set in X. Okay, so this is how one can characterize which is open and which is closed, right? In fact, once you have any two functions, so I mean that is also a very good exercise. That suppose if it's a mapping from x to r, then instead of all these functions which gives a positive value, these are continuous. So instead of all small x belongs to capital X, says that if x is strictly larger than 0, this is open in x, right? This is a very big, good exercise. You can check it. Just the same setup will happen there. So similarly, another operation that one can do is nothing but composition. So suppose that f is a mapping from x to y and g is a mapping from y to z. So both are continuous functions. Okay, so then g composition with f, this is continuous from x to z. So let us, it is also very, suppose you consider uz, this is open in z. So g composed f inverse of uz. So it is nothing but f inverse composed g inverse of uz. So f inverse of g inverse of uz, right? Now uz is open, g is continuous, so this is open set. So as is open set, so this entire one is open set. Okay. So composition is a continuous function. So that means if you have any two continuous functions or a series of continuous functions, then you can stretch get a huge continuous function from the starting one to the end point. Okay. So similarly, as it means you can stretch a continuous function. It is I should not say the word stretching continuous function. This can you can combine all the continuous functions together. So similarly, suppose we have, let's say, another function. Let's say f is a mapping from x to y, then restriction of function of any map to certain subset is also continuous, because then f inverse of, in this case, f of a restriction of u is nothing but f inverse of u intersection with a. So this is open in a. Okay. But can we extend a continuous function to certain way? There is a very important thing, that suppose if is a mapping from x to, let's say, certain set a to y, such that f is continuous function, then does there exist any g's from, so let's say, a subset of x to y, such that g restricted a, it is f. So there is a question that whether this is possible or not. So in generally there is something called gluing lemma. So the gluing lemma says that suppose we have f is a mapping from, let's say, x1 to y, and f1 is a mapping and f2 is a mapping from x2 to y, where and suppose f of restricted f1 restricted x1 intersection x2 is same as f2 restricted x1 intersection x2. But the same, then we can generalize the function g from x1 union x2 to y such that of course x1 comma x both are subset of x such that g raised to at x1 equal to f1 and g raised to at x2 equal to f2. Okay, so this is very gluing, and it is very easy. So just you define g where x1 will map to, once it is small x1 in map to capital x1 as one small x2 in to capital x2. So there is a gluing level. So let me just write it more precisely. So suppose we have g is a mapping from x1 to, let's say, x1 union x2 to y, then g of x1 will map to f of x1 and map to f1 f2 of x2. Let's say, okay, not like x, let's consider x in general. So x belongs to x1 and x belongs to x2. Okay, so once you consider a open set, and if ui, so if f in g inverse of x is exactly f1, then you can take f1 inverse. So if you, let's say, take any u subset of y is open set, so if f inverse u is exactly inside x1, then we take, sorry, g inverse u is exactly inside x1, so g inverse u we may define nothing but f1 inverse of u. We are done. If g inverse of u is exactly inside x2, so then g inverse u nothing but f2 inverse u. Okay, but if it is a x1 intersection x2, so suppose g inverse of u is I mean, this contains some element which is inside x1 intersection x2, so then g of x1, let's take small x belongs to g such that x belongs to x intersection x2, so then gx is nothing but f1 of x1, it's the same as f2 of x. Okay, so it is, then it is nothing but g inverse u is nothing but f1 inverse u union with f2 inverse u. Okay, so this is both are sets in x. That's it. Alright, so these are enough discussion with continuous functions of topological spaces. So these explanations are very useful for us to talk about something called homeomorphisms of two topological spaces. So homeomorphisms are basically that once we have two different topological spaces, but this will give me unique structure altogether. There is a specific homeomorphism. Okay, so alright, so let us stop it here, and I request you to revisit the continuous functions and if possible some basic function properties. Then in the next class we'll start the homeomorphism. Okay, so let's call it a day. Thank you very much for your patience.